Hi, everyone, and welcome back. We are going to continue our lecture on simple harmonic motion and oscillations. And we are looking now at energy and the simple harmonic oscillator. Okay, so recall the elastic potential energy that we found in a previous chapter for spring, and it is U is equal to 1/2 kx squared. Okay. Now, when we're looking at an object on a spring, the energy will oscillate between the kinetic energy of the block and the potential energy that's stored in this spring. Okay. And so our total energy of a system like this is going to be our potential energy plus our kinetic energy, which is 1/2 kx squared plus 1/2 mv squared. Now, using our previous equations of motion for simple harmonic motion and some trig identities, we find the total total energy is equal to 1/2 k a squared, where a is the amplitude and k is the spring constant. Okay. Now, looking at our images here, we see this happening. So we see the energy oscillating between kinetic and potential energy. So when we have our spring stretched or elongated to our amplitude, okay, A, our maximum position, we have all of our energy in our potential energy, okay? And then as we let go of that, it goes through our equilibrium position, okay? And at that point, we will have our kinetic energy, okay? And our kinetic energy is going to be where we have the negative V max, or our negative velocity maximum velocity, okay? And again, it passes through that, goes to our negative amplitude position, okay, our negative maximum position. And at this point, again, we have our elastic potential energy, now at negative A. Okay. And then again, we have for, once it passes that, then it goes back to our equilibrium position. Okay, or it passes through that with our kinetic energy, 1/2 mv max squared. Okay. And then again, goes back to our original position, okay, which is going to be our maximum, at our maximum amplitude here, okay? So with that, we can plot all of that information with our energy, okay? So we look down here, sorry, I'm moving something. We look down here and we see that our energy versus time, we see first our potential energy starting high, which is what we saw in this first case. Okay, and then going to 0, which is where it passes through the equilibrium position here. Okay, and then it increases again. And so this is where you'll see our U, okay, our potential energy, then our kinetic energy. Again, as we start, our velocity is 0. So we have our kinetic energy is equal to 0. And then from there, it'll increase up to its maximum, which is here, okay, at equilibrium. And then it goes down, back down to 0 as we have our maximum potential energy. So when we have a maximum potential energy, we have a minimum kinetic energy, and so forth, okay? And now with that, again, our total energy is 1/2 Ka squared, okay? We also have a position versus time and velocity versus time graph for each of these, or for this situation. So Again, our position will start at maximum amplitude, go down to minimum amplitude, and then back up to maximum amplitude. And our velocity will start at 0, go down to V max, negative V max, up to positive V max, and then back down to 0. Okay, so notice these are similar to in the last slide, I believe. Yeah. Excuse me. All right, so now let's move on to oscillations about an equilibrium position. Okay, now let's think about the potential energy that would happen in a bowl. So assume we place a marble in a bowl and it settles to the equilibrium position. Now, where do you think that the marble would settle? Okay, so if we had a bowl like this and we place a little marble, where is that marble going to go? Is it going to stay here, or is it going to go to the bottom or go to the other side? What do you think it's going to do at equilibrium? So again, like I said, the equilibrium position is going to be where it's kind of just settled down. You know, it doesn't, I kind of think of these things as lazy. And so they don't want to do any work, right? So at equilibrium, this marble will be at the bottom here. Okay, right? The bottom of the bowl. A marble isn't going to just stick to the side, right? It's going to tend to fall to the bottom of the bowl. And that's what we see here in this graph, okay? So a potential energy curve resembles a bowl, just like we have, okay? And again, if we place a marble in it, it's going to go down to here, to this equilibrium position, okay? We also see that the kinetic energy is also here, okay? And we have our total energy here, okay? But we really want to focus on our potential energy here, okay? So looking at our potential energy, say we start here, right? This is our point where we have our spring, right? So this would be our starting position maybe, okay? So this would be compressed, right? If it is at negative A, it would be, this was x equals 0. This would be x, equals negative A, okay? And then x equals positive A, okay? So we start here, and our spring would push this block over to, or through our equilibrium position and to our maximum amplitude, x equals A, okay? So it would eventually get here, right? And at that point, it will turn around, it'll turn around and go back down to the equilibrium position. Now, the brick or block will continue to oscillate between these two positions forever, right? Unless we have some kind of friction that'll slow it down. And I'll talk about that in a couple slides, okay? So this, in theory, will just continue between these two forever, okay? Now, the restoring force, which is the force that is trying to get it back to the equilibrium point, will always point towards the equilibrium position, okay? So it always wants to go back to equilibrium, okay? The equilibrium point is a fixed point, and the system will be stable at that point, okay? And it's also called the stable equilibrium point. Okay, it's got a couple of names. And graphically, let's go ahead and look at this. Stable versus unstable. Okay, let me erase this really quick. That way it's not in the way. Okay, So for a stable equilibrium point, we have this case here. So we've got, again, we're going to pretend that this is a bowl, which is just our potential energy here. And at this bottom point, which is where the ball would be placed, or the marble would end up eventually, this is going to be a stable equilibrium point, okay? Now, if we have that bowl upside down and we place a marble on top, this is going to be an unstable equilibrium point. It doesn't, it's gonna fall off, right? This point here, it may be at equilibrium, but it's not stable for that to stay there, okay? And then same thing here, we've got this curve here. And if this is the equilibrium point where this marble is, it is going to tend to slide down, okay? Notice the force positions or force directions as well. So these vectors, this is telling you where there is force, this restoring force, okay? And, or I'm sorry, not restoring force, but it's the force that's acting on these marbles, okay? So at the stable one, the forces are pointing towards each other at this equilibrium point. In this unstable one, we have the forces pointing away from the equilibrium point because it's unstable. For this other one, we have one that's pointing towards this equilibrium point and then one that's pointing away. So overall, it's again unstable. Let's look at another graph here. So for this first one, we have a stable equilibrium. So this one's stable. And notice our forces here. So these forces need to be, on this side, it's going to have to be greater than 0. And on this side, less than 0. Okay. And this means basically that this force has to be positive and this force needs to be negative for this to be stable. Okay. In this case, these are unstable because one of them is negative and the other one is also negative. Okay. And they are pointing in the same direction. So this one is unstable. Okay. So I want you guys to understand this graphically. Okay. That's my main idea here. I want you guys to understand stable versus unstable graphically. Okay. So what are these elements that are telling you that this is unstable, and what are the elements that are telling you this is stable? Okay, so remember these couple of figures and just for future reference, okay? All right, so we're gonna move on to velocity and energy conservation. Now it does go over the derivation in your textbook, but I'm not gonna go through that. And they talk a bit more about it, but just to point out energy conservation and then looking at the velocity here. Okay, so it would just be solving this equation for our velocity here to obtain this equation down here for velocity. And that's the square root of k over m times a squared minus x squared. Okay. All right, so moving on to the simple pendulum. So the main idea of a simple pendulum is to have a point mass, which is like in this figure, this point mass, suspended from a string of length L, which is from this point to that point, with negligible mass. So we don't care about the mass of the string, okay? And to understand what is going on here, we want to consider the torque on the pendulum first. Okay, so torque is, in this case, going to equal negative L times mg sine theta. Okay. And again, it we'll go through the exact derivation in your textbook if you're interested. I just wanted to give you guys a quick rundown of the simple pendulum. Okay. All right. So from that torque, we can put in the other side of the equation, I alpha. Okay. And then put alpha in as d squared theta over dt. Okay. This is very similar to what we were doing with our motion, our simple harmonic motion equation. Okay. And then plug in I for ml squared, and then solve for our d squared theta dt. Okay. And from this equation to this next one, we use the small angle approximation. Okay, so if the angle is small enough, which it is for the simple pendulum, we can just say that sine theta is approximately equal to theta. Okay, and it might say in the book, I don't remember exactly what that angle is, but I think it's something below 10 or 15 degrees, I believe. Okay, but double check me on that. But from that, we can solve for omega. Okay, and so omega is equal to square root of G over L. And so our period is equal to 2 pi square root of L over G. Okay. All right, so using that, we're going to do another example. This is 15.3. What is the acceleration due to gravity in a region where a simple pendulum having a length 75 centimeters has a period of 1.7357 seconds? Okay, so we want to know G. We have our length is equal to, I'm going to go ahead and convert this to meters. So 0.75 meters and a period of 1.7357 seconds. Okay, so let's use what we just found. T is equal to 2 pi square root of L over G. T is equal to 2 pi square root of L over G. Right? Yeah, okay. So let's go ahead and solve this. So we want to find G, so let's do that first. We'll square everything. We've got T squared is equal to 4 pi squared L over G. And so G is going to equal 4 pi squared L over T squared. So let's put this in here. We have L is equal to 0.750 meters. Okay. Over T, which is 1.7357 seconds, and square that. Okay, so we just need to put that into our calculators. So we've got 4 pi squared times 0.75, and then we divide that by 1.7357 squared. So G, the acceleration due to gravity, we get 9.8, how many digits do we have? We have that many. So I can say 28 meters per second squared. So we just found the acceleration due to gravity using the simple pendulum. Okay, and this is actually fairly good given that the actual is 9.81 meters per second squared. So that's pretty good estimation. Okay. All right, now that was a simple pendulum. Well, what if we have a physical pendulum? Okay, this is going to be any object whose oscillations are like the simple pendulum, but can't be modeled as a point mass on a string. So there is some sort of mass distribution that has to be included into the equation of motion. Okay, so it's not necessarily a simple string with some little point mass. It is some physical object, okay, with a weird shape maybe, like this one, and then it's swinging from some point here. Okay, that's its rotational axis, right? Or its pendulum axis, I guess. Okay, so you have to use different equations of motion in order to do this. And again, I'm not going to go through the detail, but this is what you end up with. So this is our omega. It is equal to square root of mgl over I. Remember, I is inertia. Okay. And then our period is equal to 2 pi square root of I over mgl. Okay. All right. Quickly wanted to talk about damped oscillations or dampened oscillations. And this is when we have friction of some kind that acts to dampen the motion. So it goes away or needs more force to continue that motion, okay? So this is actually what really happens in our world that we can see in front of our eyes, okay? Because we don't have perfectly frictionless anything, right? There is always some sort of friction involved. So what happens is, say you have, I don't know, try to think of an example. Well, let's look at the guitar string that we talked about earlier. So a guitar string, you pluck it and it'll, oscillate for a while, but then it eventually goes away, right? That's because we have some sort of friction that's acting on it. In this case, we have some object suspended in some kind of liquid on a spring. And again, over time, it will go back to its equilibrium position. Okay, just like the cube earlier that we had attached to a spring on some frictionless surface. Well, if we introduce friction and move that block and let it go, it's going to eventually stop moving and go back to its equilibrium position. So again, like the marble, right? We had a bowl, right? We had a bowl, and if we place the marble here, it's going to go back and forth until it dampens enough to stop down here at the bottom at its equilibrium position. Okay, and we see that in this graph here as well. So this is position versus time. Okay, and so we start at our highest amplitude, our maximum amplitude, go down to almost our minimum amplitude, and it's already starting to dampen. Okay, it doesn't go all the way down to the bottom here, just above. Okay, and then again goes back up, and it's trying to hit the peak again, but it doesn't. So we have this damped oscillations, okay, that happens, and this is what it graphically will look like. Okay, and eventually it will, phase out and just be at x equals 0, okay, or equilibrium position. Okay. All right. So one more thing that I want to talk about is called resonance. Now, we'll need to first understand the natural frequency of a system, and that is going to be the frequency at which the system oscillates if it's not affected by driving or damping forces. Okay, so it's just the natural frequency that this object will oscillate. Okay. Now, the resonance is when the driving of a system with a frequency is equal to its natural frequency. Okay. And a system that is being driven at its natural frequency is said to resonate. And you guys have probably heard of resonance, maybe, or resonate or something like that, possibly. And I just wanted to point this out. So this is at when it is resonating. So resonate here. Okay. So this is at F naught, or its natural frequency. And notice the change in the amplitude. So if we have a low frequency with this ball attached to a person's finger, just kind of going up and down, the ball will have some sort of amplitude here, some maximum amplitude. And as we get to its natural frequency, it'll begin resonating, or kind of like at its peak. That's kind of how I think of it. Okay. So it will be at its highest amplitude here. Okay. Then when we have a really high frequency, it again goes back down to a smaller amplitude here. Okay, so just understand what that natural frequency means for the resonance. Okay. Yeah, how those relate. Okay, the amplitude and this resonance. Okay. All right. That is all I have for you this time. I was hoping for it to be a little bit shorter, and I will have all of your homework and everything up soon. So I will see you in the next video.